Last time we were talking about the rarity finger action. There are many ways to write it down. The simplest one is this one, with the epsilon tensor. But you know that epsilon times gamma 5 can be written in other ways, and it's a little bit annoying to show that this is equivalent to that, and that that is equivalent to the other one. If you want to do it, you can do it as an exercise. Otherwise, it's not really necessary, because don't even think that these kinds of exercises are so useful, because it's really algebraic stuff. So it's not an exercise for the exam. We have to write down the propagator of the spin 2/2 field. So the propagator is a matrix P mu nu such that multiplying by Q nu rho is equal to I times the identity. And I just write the answer, and then we check that it is okay. I divided by P squared minus M squared times the following complicated matrix, P slash plus M times eta mu nu minus P mu P nu divided by M squared, plus 1/3 gamma mu plus P mu divided by M times P slash minus M gamma nu plus P nu divided by M. And okay, there is a pole, but we want to show that there is no pole when we contract with P or gamma. And actually, again, this is a way to build the propagator. Find that there is a unique propagator that has this property, and then you invert the propagator and get to the action. Again, there is little to do. It's non-renormalizable when you have massive fields with spin larger than 1/2. Renormalizability is violated. So let's check P mu nu times P nu, and that is equal to what? I divided by P squared minus M squared. And let's see what we have in between. So if we multiply this by P mu, we have P mu, the usual thing we saw the other time. So this is order, this already goes away. So there is a P squared minus M squared. When P squared is equal to M squared, it is 0. So the only thing is the rest. And the rest is 1/3. So we have to contract with P nu gamma mu plus P mu divided by M. And then we have P slash minus M. And you see that what you get here is P slash plus p squared divided by m squared. P squared divided by m. So on shell, this is on shell, which means on the pole, this is p slash plus m but then when you multiply p slash plus m times p slash minus m, you have p squared minus m squared. So you have p slash plus m here and a p slash plus m there, minus m plus m. So this is p squared minus m squared. That cancels the pole, and so this is order 1, and there is no pole. This was easy. The other one, well, there is maybe some gamma matrix commutation to do, but can do it. P mu gamma nu is equal to I divided by p squared minus m squared, p slash plus m. So gamma mu here gives gamma mu minus p mu p slash divided by m. P slash divided by m. And that's not something we can really plus m squared. That's not something we can drop. We have to keep it. Then we will see plus, let's copy the rest, 1/3 gamma mu plus p mu divided by m times p slash minus m times, so if we contract with gamma, we get 4 plus p slash divided by m. Gamma mu is equal to 4. Okay. I divided by p squared minus m squared. And one thing here, p slash here p slash can be written as p slash minus m plus m, and here p slash can be written as p slash plus m minus m. Why? Because p slash minus m here will multiply p slash plus m and cancel the pole, so we can basically drop this. Here we can drop that, because p slash plus m will multiply p slash minus m, and that p squared, that is equal to p squared minus m squared. So basically, the first case p slash is equal to m, in the second case p slash is equal to minus m. And when you do that, you get some simplification. So we have p slash plus m times gamma mu minus p mu divided by m plus 1/3 gamma mu plus p mu divided by m times p slash minus m times 4 minus m divided by m, so times 3. And that cancels the 1/3. Plus, so what we are neglecting are things of order 1. Okay. Now, I divided by p squared minus m squared. Let's see what we get there. Let's check p slash gamma mu plus gamma mu p slash. We can use this is an anti-commutator for those two terms. So this one plus this one. And we use the Dirac algebra, flat space. So this is 2 p mu. Then there is p slash p mu divided by m. Then there is m gamma mu. And then there is minus p mu m times pm divided by m. P mu divided by m. It's minus p mu. The other one, what we remain with, minus m gamma mu plus p mu divided by m p slash minus p mu. So that's 2 p mu minus p mu minus p mu minus p slash p mu divided by m plus p slash p mu divided by m plus m gamma mu minus m gamma mu. So that is how the propagator is built, basically. It's a long thing because you have to list all the terms you can build. That's a little bit annoying with these gamma matrices. But if you want to make the exercise in the case of spin 2, that can be easier. Massless spin 2, which means write down the most general thing that you can write here. So 1 divided by p squared minus m squared. Then you write down the most general thing that you can write with p, mu, and delta, mu nu, or eta, with the right symmetry properties. And then you just impose that this has no pole on shell. That's it. And then you will find this propagator uniquely with no other thing. And then when you invert that propagator, you will find the Pauli fields action. Now, in the case of the Pauli fields action, we already knew what the massless limit was, and that was the quadratic part of the Einstein action. Here, in the massless limit is sort of new. Massless limit is the one where you gain a gauge freedom, basically. So we can use this form here. And in a massless limit, you have this. This is the action, the free field limit of the action of the gravitino, which is the fermionic superpartner of the graviton. So basically this, I think, is the Raritas ringer, the properly known action. What you have here, you have a gauge symmetry. What is it? Well, you see that it's like a vector. This is like an F mu nu, because you have partial rho psi lambda, but you have anti-symmetry in rho and lambda. So it's like having partial rho psi lambda minus partial lambda psi rho. And that means that if you make the following gauge transformation, the action doesn't change. And the same for psi bar, of course, because you can write an equivalent action where the derivative up to boundary terms, up to a partial integration, you can turn the partial derivative to the left, and then you will have a field strength. You will have partial rho psi bar mu minus partial mu psi bar rho, because you also have anti-symmetry in mu and rho. So this is a symmetry where epsilon is what? Epsilon is a spinor. So this is a simplest case, a trivial case of a spin 3/2, which is a spin 1/2 with the derivative. And that is, of course, not a physical degree of freedom. For this symmetry, you need a gauge fixing. Typical gauge fixing conditions. One is this. It's like the Lorentz gauge in electrodynamics. Partial mu psi mu is 0. With the residual gauge freedom, that is what you get by taking the variation of that. So instead of partial lambda, you have, instead of psi lambda, you have partial lambda psi. That is the residual gauge freedom. But there is also, this is a derivative condition, but there is also another condition, gamma mu psi mu equals 0. This one is algebraic. What is the difference between an algebraic gauge fixing condition and a non-algebraic one? Since it is algebraic, it could be solved by eliminating some components without having derivatives disturbing the solution. And but it's not normally done, so it's not particularly useful. And the residual gauge freedom is what? Again, you have to replace make a gauge transformation of that, psi mu becomes partial mu psi. So you have partial slash epsilon going to 0 equals 0. So this is the residual gauge freedom. And when you quantize it with the rules that we have described, you will propagate just the right degrees of freedom for a spin 3/2 particle, massless in this case, and in that case it has, can show that it has two helicities. In 4 dimensions. So this supersymmetry is a symmetry where you have supposed symmetry between fermions and bosons. So for each fermion there is a bosonic partner, and for each fermion there is a for each boson there is a fermionic partner, and for each fermion there is a bosonic partner. So this can work only if, since the graviton has two helicities, the gravitino must have two helicities. And then you can build a theory which contains the graviton and the gravitino. Otherwise, you would need more things to balance the number of degrees of freedom of bosons and fermions. And only in that case, you can hope to build a theory that has this extra symmetry. What is the supersymmetry? Well, the gravitino actually enters in what is called supergravity. And supergravity is the Einstein-Hilbert action plus the covariantized form of this, which has a local symmetry that is equal to this one, plus corrections to have a covariantized form of the local symmetry. So when you include the two things, you will have diffeomorphisms, local Lorentz invariance, and you will have this extra local symmetry, and that is called local supersymmetry or supergravity. So this is the symmetry, the gauge field of the supersymmetry is the gravitino. So you have to covariantize the derivative also in the sense of this symmetry. It's a long construction. If you will have the chance to see it, you will see that in supersymmetry and supergravity you will be buried by very, very long formulas. If you have been annoyed by the formulas we have seen in this course, these are nothing respect to those you have to do in supersymmetry and supergravity. But luckily, there is no evidence of supersymmetry, so you can save the time. In 2012, I recall that the Higgs field was the minimum thing that CERN was supposed to find, because the purpose was to find supersymmetry. Not the Higgs field. Yes, it was one of the things, but this was the minimum thing to claim, to justify the amount of money that was spent. There was no sign of supersymmetry, and since then, much fewer people talk about it. You cannot imagine how many years, people, and papers have been written on supersymmetry. Before moving to another subject we have to talk is to talk about submanifolds, a little bit of differential geometry for submanifolds, because we want to treat the boundary term of the Hilbert action. And the boundary of R4 is like a sphere, so it's a submanifold. Before going to that, let's make some complements, talk about some additional comments about gauge fixing and a few other properties that we have seen and we have not had the chance to complete. Well, they were complete, but we can add a few notions that you will have the chance to meet sooner or later. For example, what about the gauge fixing for the field line? We have not seen that. So additional comments or remarks. About gauge fixing. There is an algebraic gauge fixing condition for the metric without the field bind also, and that is called the synchronous. Hope I write it correctly. CH, I think. Synchronous gauge. That is G00 equals 1 and G0I equals 0. So G mu nu has a space part and 1. So the only thing that matters here is Gij, which we might write as minus gamma ij, and then minus gamma is the space metric, because our signature in flat space, that would be Gij would be minus 1, minus 1, minus 1, so gamma ij would be the, the metric. So this is an algebraic condition, and it's easier to well, some things simplify, but it's not a very practical condition. So in this case, the metric is, the time part is the same as in flat space. The field bind gauge conditions for the field bind. Let us recall that E mu A, well, so the first, let's say most popular gauge condition is the symmetric gauge. What does it mean? That basically E mu A should be symmetric. Now these two indices are different indices, so that means that you have to break everything basically. You break not only Lorentz symmetry. So what gauge conditions for the field bind mean? For local Lorentz invariance. For local Lorentz invariance. Now, since we have to break, gauge fixing has to break all gauge freedom, even diffeomorphisms, you can break both at the same time. Don't need a gauge fixing for the local Lorentz symmetry that does not break diffeomorphisms. So this one breaks both. And it says that E mu A should be symmetric. So let's say that you have somehow to exchange the indices mu and A. So you have to use something like this delta function with mixed delta tensor with mixed indices that break everything, both diffeomorphisms and Lorentz invariants. If you expand around flat space, what do we do normally? We have g mu nu equal eta mu nu plus 2k phi mu nu. And well, you know that in terms of the field bind, G mu nu is E mu A, eta E B, E nu B. Basically, apart from the eta, E is the square root. So first, in flat space, forget about this, eta mu A would be, E mu A would be eta mu A. And then you have plus k, 1k, because it's a square root, phi mu A. You have to solve that. That is a square root, basically. Plus, and then you will have an infinite series in expansion in powers of kappa phi. But to the lowest order, the one that will give the quadratic part of the action, that's just this. So to the lowest order, this symmetric gauge is the assumption that phi mu A is equal to phi A mu A is equal to phi A mu. Actually, this is built in here, because if you define phi mu nu like that, it's already symmetric. So there is, let's say it better. If you define phi mu nu like that, then when you want to find the solution of this will not be the unique solution, because any Lorentz transformation will, local Lorentz transformation will preserve the structure here in the metric eta. So that's not the unique solution, and you can choose this to be the solution in the symmetric gauge. So let's say it better. This is the solution in the symmetric gauge. Solution is not unique because this equation is invariant under local Lorentz transformations that act only on A and B and do not know anything about mu and nu. So it cannot be unique. But this is the solution in the symmetric gauge, the solution of star in the symmetric gauge. Alternatively, we can start from this expansion in flat space too. So redefine the expansion around flat space. As this exact if this is the expansion around flat space, we do not know anything about phi mu a. Could be not necessarily symmetric, should not. So impose the symmetric gauge which means that phi mu a should be equal to phi a mu, and then g mu nu is what? Is the square of that. So the square of that will be g mu nu will be equal to eta, the double product, which is 2k phi mu nu, because it will be phi mu a, but there will be a eta ab eta a nu, so it will be phi mu nu, and there will be a square, kappa squared, because square of that, which will be equal to phi mu a eta ab phi nu b. And that's exact, but it contains these quadratic terms. Okay, that's also exact. You don't have an infinite thing, but you have to deal with with non-polynomial things with gravity. Now, the symmetric gauge is algebraic. One good feature of the symmetric gauge is that it does not contain derivatives. So it can be solved without too much effort. It's enough, for example, to make this expansion around flat space and say that this is a symmetric matrix, phi mu a, and that's it. You already have imposed this gauge. There is another nice thing about this gauge fixing condition, and that is that you don't even need the ghost part. You remember that when we had a gauge fixing, we had the gauge fixing and the ghost. So now we make a comment on that, because that is a very nice property of this gauge, which is why it is used. And the reason why it is algebraic, the ghost part drops, is that the gauge transformation is also algebraic. There is no derivative of the parameter. It's not like delta A mu is equal to d mu A, d mu lambda. That's not algebraic. The gauge transformation has a derivative. So here you get rid of everything basically with no effort. It's a sector that you can handle quite nice. That doesn't mean the formulas will be simple. Calculations with this, with the field bind, which you have to do because with the fermions you have to do it necessarily, will be very long, but there are computer programs that can handle these things. So let's recall how the gauge fixing is performed. So L goes into L plus 1 divided by 2 lambda. Let's say you have some gauge fixing, some number of gauge fixing with some index A. Actually, you may have a matrix there, because it's not, for example, with G mu you have to raise and lower. Maybe we can put a matrix here. And then you remember there is a ghost term, which will be the variation. So you can define some anti-ghosts with a lower index. And then you have the variation of your gauge fixing condition with respect to your fields. And the fields have their own indices, which are whatever they are. And then you will have the infinitesimal transformation of those with some parameter that you call C, and that will play the role of the ghost. It's a little bit cryptic, but in the end, it's not. So this is the gauge transformation. So let's say GA are the gauge conditions, some functions of phi. Typically they are linear in phi. Phi I are the fields. And then you will have anti-ghosts, and Fadeev-Popov ghosts. You will have as many symmetries, as many gauge fixing conditions, of course, because the gauge fixing conditions should precisely break those symmetries. So you can imagine that this M is equal to 1, or some eta, typically. You can choose actually whatever you want. But if you put something here, you might have to modify this. But let's assume that MAB is a constant matrix. Well, there is an equivalent way to write it. By means of some auxiliary fields, which normally are called B, capital B, that are Lagrange multipliers for the gauge conditions. So just like that. Plus BA, some matrix that now we work out. And the ghost Lagrangian is unmodified. So this is a standard trick if you have a quadratic thing here, so ignore M. M is just a constant, it's just a matrix that's there. But if you have a quadratic thing, you can introduce an auxiliary field, and it's equivalent because if you work out the field equations for B, as you remember from, because we did it, but we do it again now. If you work out the field equations for B and insert the solution back, you will get that. So that's how we determined what NAB is. BA equations, that is 0 is equal to GA plus 2NB. Let's use the matrix form. So that means that B is equal to minus 1/2 n to the minus 1 G. And that means that this thing here goes into what? When you insert the solutions, you will get BG minus 1/2 G n minus 1 G plus B and B, that is plus 1/4 G n minus 1 n minus 1 G. That's it. That is minus 1/4 G n minus 1 G. And this tells you what the relation between M and N should be. M divided by 2 lambda must be equal minus n minus 1 divided by 4, or n minus 1 is equal to minus 2 over lambda m, or n is equal to minus lambda over 2 m minus 1. So another way to insert the gauge fixing is this one. Let's stop 10 minutes and then we'll move on.